Hi, in this video we are going to look at the different heap operations and its complexity analysis. Heap is a very useful data structure which is used along with many algorithms. Kruskal's algorithm is one of the algorithms which can be implemented using heaps. So the understanding of heaps and heap operations and their complexity is very important for the understanding of Kruskal's algorithm. The outline of this presentation is going to be like this. We will initially look at the basics of binary trees, which are very essential for the understanding of heaps, and then we will come to heaps. We will discuss the heap data structure with two varieties, max heaps and min heaps. Then we will look into the different kinds of heap operations which are commonly used and analyze their complexity. Now let us try to understand some of the different types of binary trees available. The first one we will try to understand is about a full binary tree. A full binary tree is a binary tree in which every node other than the leaves has got two children. So if you look into this diagram, the leaves are 3, 4 and 2, and the nodes which are the internal nodes are 0 and 1. So if you look at 0, 0 has got two children, that is 1 and 2, and 1 is also an internal node. It has got two children which are 3 and 4. So this is a full binary tree. And a complete binary tree, we'll try to understand what is a complete binary tree. A complete binary tree is a binary tree in which all the levels are completely filled except the last level. And in the last level, we can have gaps in the right side. This means that we will be filling a complete binary tree from top to bottom, left to right fashion, which means we will be initially filling up this root node, then we will be coming to the left side, then we will be moving to the right side of that level. So that level is completed, and then we will come to the next level. We will fill this up, we will be filling this up, and so on. Now let us try to understand what is a perfect binary tree. A perfect binary tree is a binary tree in which all the internal nodes have two children and all the leaves are at the same depth. So in this diagram you can see that all the leaves here are in the same depth, and also all the internal nodes are having two children. If you look at the node 0, it has got two children, 1 and 2. If you look at 1, it has got two children, 3 and 4. And if you look at if you look at 2, it has got two children, 5 and 6. Suppose if I am adding two more nodes to this full binary tree, and I need to verify whether it is again a full binary tree. In this setting, we can again verify that every internal node has got two children. So every internal node has got again two children. So this is again a full binary tree. But is it a complete binary tree? The answer is no, because in a complete binary tree you have to fill the nodes from top to bottom, left to right fashion. So here you can see that these nodes are not filled. Also these nodes are not filled. So this is not a complete binary tree. It can become a complete binary tree if these nodes are also present. These nodes and also these nodes. So the understanding of a complete binary tree is very essential to understand heaps, because heap is a complete binary tree. In a complete binary tree, it is easy to verify that if there are n nodes, the number of leaves will be roughly n by 2. And the number of internal nodes, that is the nodes which are not leaves, are going to be roughly again n by 2. Let us look at an example and clarify this. That is
the number of nodes are n, the number of leaves will be n by 2 and the number of internal nodes will be n by 2. It is also important to note that for a complete binary tree with n nodes, the height of the binary tree will be roughly log n. And this property is used when we analyze the complexity of some of the heap operations.
The figure that you see here is a complete binary tree. You can see that the nodes are filled from top to bottom, and in all levels it is filled from left to right. So in the last level you can see that all the left portion is filled, and now there are some gaps in the right side, which is acceptable.
Now in this binary tree, if you count the total number of nodes, it is 12. And if you are counting the number of leaves, as you can see here, 1, 2, 3, 4, 5 and 6. So the total number of leaves is 6, and the total number of internal nodes are also 6. We can see that if there are n number of nodes, the number of leaves is n by 2, and also the number of internal nodes is also n by 2 in this example. Let's now add a few nodes and check whether this is holding. So if I am adding one more node to this tree like this, and now let's look at the values. Here the total number of nodes is 13, and the total number of leaves you can see 2, 4, 6 and 7, and so the total number of nodes, internal nodes, is 6. We can add a few more nodes and verify that this property is roughly holding. In this example you can see that there are 31 nodes and the number of leaves are 16 and the number of internal nodes are 15. Now let us try to understand what is a binary heap. As told earlier, it is a complete binary tree which will satisfy the heap ordering property. Based on the ordering, there are two types of heaps, min heaps and max heaps. In a min heap, each node, the value of each node will be greater than or equal to the value of its parent. And so, the minimum value will be stored in the root. Similarly, in a max heap, the value of each node is less than or equal to the value of its parent. So, the maximum value will be stored in the root. Now, this is an example of a max heap. In this tree, the root is 13 and its children are 24 and 7, which are less than 33. And again, the children of 24 are 12 and 5, which are obviously less than 12 and 5. The children of 7 are 6 and 5, which are less than 7. And this is also a complete binary tree. And this will not be a max heap if you have some node like this and some value like this here. So this will no longer be a max heap just because the values are not filled from left to right. Now this is an example of a min heap. Here you can see that the minimum value 4 is at the root and the children of 4 are 10 and 12, which are obviously greater than 4. And this property holds for every subsequent nodes. So if you take an example, in case of 15, 19 and 18 are its children, which has got a value less than 50. Now that we know about a heap, it is important to know about the different heap operations and their complexity. And these are the major operations performed on a heap. The first one is to extract the min or max from a heap. The second operation is to heapify. We will discuss what is heapify in our next slides. And given a heap, how can you insert a new value into a heap? And another important thing is how to build a min or max heap from a given data. Now let us look at the operation of the extract max or min. In this example, we are looking at extracting max from that is extracting the maximum value from a max heap, and the procedure is also very similar for extracting the minimum value from a min heap. The only thing that we need to do is that we have to go to the root and then extract the value, as we already know that the max or min value will be stored in the root. So if you also want to delete that particular value from the heap, then you have to do some additional work. That is, normally what is done is that, so if you want to take 33 away, and you cannot maintain a blank space here. So what actually you are going to do is, you are going to take this value, the last value in the heap will be taken from here and it will be put here. And now the heap becomes unbalanced because the property of a max heap is no longer maintained. So now we have to make it in order. So if you also do this delete operation, then we want to make the heap in order again. So doing that is called Heapify. The operation is called Heapify. So we will look at Heapify and how it is done in the next slide. So in this case, extracting max or min from a given max heap or min heap will not take any time. It is just go to the root and then extract it. So the complexity will be order of 1. So you may it is also very important that to understand that heaps can be maintained as an array. In this case, you can think of an array like this, where the values of the heap are stored like 33 in the order that you see there: 33, 24, 7, 12, 5, and so on. And in the case of an array-based storage, extracting max is very simple. Go to the first location and then take this 33. As we have already told, the Heapify operation refers to rearranging of the heap to maintain the heap property once it is disturbed. So given a max heap or a min heap, at some point of time, for example, if you are inserting a node, or if you are deleting a node, or you are extracting the max or min from a heap, then the property of the heap property will be lost. So in such a case, we have to again make it a heap. So this process is called Heapify. Now let us look at an example of Heapify operation and let's try to analyze its complexity. Now suppose that we want to extract max from the given max heap and then delete it from the heap. Then what we need to do is that we have to extract this 33 from here. So what will happen is that you will have a blank space here. So again, what you do is that you delete 11, that is the last node which is present in the heap, and then put it here, put 11 here, so that 33 is deleted. But the problem is that the heap is no longer a heap. So we want to modify this or rearrange this to make it as a heap. So what we are doing, what we want to do is that we have to compare the value, the new value which is now at the root, which is 11, with its children. You can see that its children are 24 and 7. Now the maximum value of this children, now we can know that 11 is less than 24. So out of this, the maximum value is 24 and 11 is less than 24. So what we need to do is bring 24 there. So now the tree will become something like this: 24, 11, 7, 12, 5, 6, 5 and 10. Now again, there can be problems. So now 11 came down to the next level, and then again you have to check for any repairs there. So if you are looking down, you can see that 12 is greater than 11, and so you need to swap 12 with 11. That means you have to swap 11 with 12, something like this. So you have to take 11 from here and swap it with 12. So 12 will be on the top. 12 will come here and 11 will go here. And now again you have to check to the next level. The node which is present there is 10. So now this maintains a heap property at each node. So now this Heapify operation is completed. Now to analyze the complexity of Heapify operation, we want to carefully look at the method that we follow here. So suppose that we bring the last node to here, and then there is a rearrangement happening in this direction, and then after that again the tree is disturbed, again there is a rearrangement, suppose it is happening in this direction, and so on, and it can even go to the leaves. So if in the worst case this rearrangement, that is comparing and swapping, will happen till the leaves. So how many number of such comparisons and swapping are happening is to be calculated. So in the worst case, you have to do the comparison and swapping till the end. That means up to the last level. So it is, if you count the number of such operations that you need to do, it will be at most log n, because log n is the height of the tree, height of the tree which has got n nodes. If the tree has got n nodes, log n will be the height of the tree. So the path that you trace like this cannot be more than log n. So the complexity of Heapify operation is going to be order of log n. Now for performing an insert operation into an already existing heap, what we have to do? So given a value, we want to insert it into the given heap. Suppose if I am asked to insert 44 into this heap, what I will try to do is that I insert it into the last unfilled position and see if the heap property is maintained. If it is not maintained, you have to call the Heapify function. In this case, it is not holding. So what you want to do is you have to swap 44 with 5. So 44 will come here and 5 will come here. And now again check for the property, heap property, and again it is not maintained. So what you want to do is that you want to swap 12 with 44. So 44 will come here and 12 will come down, and again check the same. Now you can see that again there is a problem. So what you need to do is bring down 24 and 44 will go up. So now the new heap has become something like this: 44, 24, 7, 11, 12, 6, 5, 10, 33 and 5. So this maintains a heap property. Now in doing so, again it is similar to, the complexity is similar to the Heapify operation. So you can see that you had to swap this value, number of swap comparisons and swapping is performed to all the levels till you reach the root. It means that you are tracing the height of the tree. So the number of comparisons and swapping that you are doing is proportional to the height of the tree, which is log n. So the complexity of an insert operation into a heap in the worst case is given by big O of log n. Now that we know about insert and Heapify operations, we can study about how to build a max or a min heap if you are given with some values. So the naive way or the naive idea is to think that you have to insert the values, and then if heap ordering is lost, you have to heapify. So if you are given with n nodes, you have to perform n insert operations, and n times you have to insert, and every time you may have to do a heapify. That is in the worst case. So if you are performing n operations and each time you are doing a heapify, then the heapify operation itself will take log n time. So the normal way to think about the complexity of build max heap is that it will be order of n log n. But if a more careful analysis is done, we can see that we can reduce the complexity to order of n. Let me try to explain how this is done. If you are given an array which is not ordered, and what you want to do is to create a heap out of this array. So what we can actually do is that, suppose if it has got some values, say x1, x2, x3 and so on, so I will fill all these values arbitrarily into these positions, okay, and I will fill all the values. And now that I have filled all the values, if you look into the leaves are already holding the min heap or max heap property because they don't have any children. So we need not do anything on the leaves. We are only bothered about one level above the leaves. So as you know, there are n by 2 leaves for a tree with n nodes. So for n by 2 nodes, we don't need to do anything. So what we want to do is that we have to look into one level up, which contains n by 4 nodes, and then do a comparison and swapping if required. So how many such comparisons and swapping at the max is required? Because you have n by 4 nodes, you will have only n by 4 operations to be done, one operation each for each node. So if you perform n by 4 such operations, then you are completed at that level, and then there can be disturbances in the next level, which again contains only n by 8 nodes. So you go to the higher level and then perform the repairs. In this case, once you perform the repairs, you may have to do 2 repairs in each node. So in this case you have to perform 2 repairs each. So totally you have to perform 2 into, you may have to perform 2 into n by 8 operations. Let me write this, 2 into n by 2, n by 8 operations. And in the next level you may have to perform 3 repairs. Okay, so you may have to have 3 operations on n by 16 nodes, and so on. Now let us analyze the complexity of these operations. So what we have discussed is that we don't want to disturb, we don't want to do anything with these n by 2 nodes. We want to check with these n by 4 nodes if they are in the correct position. So, and if at all they are not in the correct position, we want to make a comparison and a swap. So at the max, as there are n by 4 nodes, then you need to do only n by 4 comparisons and swapping. Suppose comparisons and swapping will take a constant time, say c. Then to perform comparisons and swapping at this level for each node, it will take n by 4 into c into 1, because you need to only do one comparison and swapping for each node. Now that level is completed, and then you now go to the one level up, where you have n by 8 nodes, and in all those n by 8 nodes you may have to perform 2 comparison and swapping operations, which means in the next level, as there are n by 8 nodes, you need to perform n by 8 into c into 2. And if you have some higher levels, then you need to perform n by 16 into c into 3, and so on. So let me write this in a systematic manner. So what we need to do is, on n by 4 nodes, you have to perform one operation. Each will take c, a constant time c, and then you may have to go to the level up, and then there will be n by 8 nodes, and there you have to perform 2 operations, each of which is going to take c time, and then this series continues, and we can generalize this as, say, n into 2 raised to k plus 1 into k. Kc. So I can take n by 4 common here, n by 4 and c outside, then it becomes n by 4 into c into 1 by 2 raised to 0 plus 1 by 2 raised to 1 plus etc. 2 by 2 raised to 1 plus 3 by 2 raised to 2 plus etc. plus k divided by, say, 2 raised to k minus 2. And generally this series is a series which is a well-known series in maths, which is a constant. I think that it cannot take a value which is greater than it will be always, this value will be always less than 4. So what we are getting here is n by 4 into c into 4 at the max. So you're going to get a complexity of complexity here is going to be order of n. And this is a very important thing, is that the complexity of building a min heap or a max heap from a given set of values is going to be order of n.